Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Dave Ansell. Hello to Jake, who's on the A14, Dr. Dave. He says, hi Dave, can you answer this? If the sun is losing mass, will the overall gravity that affects our system change over time?
I think the simple answer is yes. The sun is losing mass very slowly, both because as it releases energy in the form of light, and because Einstein said that energy equals mass times speed of light squared, as it loses energy, it will lose mass very slowly. It's also losing mass because its atmosphere is getting blown off all the time in what's called the solar wind. This is actually what causes the auroras up at the North and South Pole. This is basically the sun's atmosphere, made out of mostly hydrogen and helium atoms, is being blown off, especially in big eruptions called solar flares, but it's getting blown off all the time and more slowly. And this flies through space and smashes into our magnetic field, which funnels it into the North and South Pole. And when these little the nuclei of these atoms, especially hydrogen atoms, and also electrons, smash into the atmosphere, they make the air glow in the same sort of way as as it makes gases glow in a fluorescent tube or a neon tube. This is what's causing the aurora borealis and aurora australis, I guess, in the southern hemisphere. And that will lose weight, but it's losing mass very, very slowly. So it will have some effect. The Earth's orbit will, as the sun loses mass, the Earth's orbit would get larger because there's less holding it in. But it's a very, very slow effect. I don't have any numbers off the top of my head, but yes, it is slowly changing things, but very, very gently, and the Earth will slowly move away.
All right. Dave, we've got Dave on the line. Hello, Dave.
Hi, Sue.
Lots of Daves everywhere.
Yeah.
You're through to Dr. Dave.
Well, Dr. Dave,
yeah.
I've got a question for you. The piezo ignition, which is in electronic lighters and stuff.
Yeah.
How does it work, firstly?
I'll start off with that one, otherwise I forget what you asked me in the first place. Actual piezo ignition works by, you get a crystal of something like quartz. I don't know if they're always quartz, but quartz definitely does it. And when you bend quartz, it moves charge inside the crystal. So one side of it will get positive and one side of it will get negative. And this actually doesn't move very much charge, but it will actually produce a very, very high voltage, thousands of volts. So if you attach two wires, one to each side of that, and then make them come close together at the other end, then when you bend the quartz crystal, you get a little spark at the other end. And that's what you use to light the gas. The same process works the other way. If you apply a voltage to a quartz crystal, it'll bend too. So I don't know if you've ever seen, you sometimes get little transducers in cheap toys which look like they're sort of little tiny loudspeakers. They're like little flat things which are sort of brass coloured. Yeah. Those have got a little quartz crystal in it, and when you apply voltage to it, it bends. Therefore, if you apply a music signal to it, it will basically act like a loudspeaker as it bends backwards and forwards and vibrate the air. And you can hear it.
Well, now I'll tell you what led me to ask you the question.
Okay, go for it.
I pulled up one of them piezo lighters to pieces,
yeah.
Right, trying to figure out how it worked. I got the actual mechanism between finger and thumb,
yeah,
and I pressed it, and I got a hell of a belt. It was worse than what you get off the mains. That went up my fingers and up my arm, and it was like, must have been at 30,000 volts or something.
I mean, they do produce light. So you're bending this crystal somehow, and it was building up a big charge, big voltage, which was going through you. Yeah, it would give you a hell of a shock, I'd have thought.
It did. I can't believe how such a little thing, because there was no battery in there. And I thought, well, where's this electricity coming from? Why can't this electricity be enhanced and stored somehow and used for such a little tiny cheap thing to create so much electricity? Isn't it possible to actually use that electricity for something?
Apart from sparks,
yeah.
You can produce very high voltages, which produce lovely big sparks. The thing is, it's very, very low currents, and power is voltage times current. So because there's such a small current, there's very low power. So it's actually not very useful for anything other than sparks. the opposite of it is being used in all sorts of places. As people you make actuators to move things very accurately, and let's put loudspeakers I was talking about earlier, and more clever loudspeakers. But actually, for generating power, it's not very efficient. It's probably only a few % efficient of the energy you put in will come out as electricity.
But if you squashed a million of them at the same time, you'd have enough electricity to light up the world.
Well, you might be more likely, you probably have about enough electricity to light a small light, but a few light bulbs, because they're just not. Yeah.
Thank you very much.
And don't do that again. It's dangerous.
I'm now going to go and pull my microwave to bits.
All right. Well, hopefully you'll be with us again next week, then, Dave. Thanks very much.
See you later.
Bye.
Bye.
And John in Bedford, Dave, asks, on average, how far does sound travel before it's audible? That is, if you stood in an open space and shouted as loud as you could, approximately how far away could it be potentially be heard?
That's one of those questions where the easy answer is it depends. It's going to depend on an awful lot of things. I mean, first of all, of course, how loudly you're shouting and how much background noise there is, because if it's an absolutely still day, very, very quiet, there's no one playing with a drill next door, then the people who are listening will be able to hear much fainter sounds than they would do otherwise. There are all sorts of other things which affect it. One of them is pitch. High-pitched noises, because they're basically high pitch means it's a rapid vibration. And the rapid vibration is moving the air backwards and forwards more quickly. And so you get more friction within the air, so it loses energy more quickly. High-pitched sounds tend not to travel as well as low-pitched sounds. And this is why if your neighbours are playing loud music, you always hear the bass rather than the treble, because the bass is deep, the vibration's much more slow, so it loses energy more slowly, so it travels further.
Oh, right.
And also, I always find if I'm listening to music which is played too loud on speakers and it's clipping and it sounds really horrible, if you put stuff in your ears, it tends to kill the high-pitched noises and make it sound a lot better. But that's just a side thing.
It's just a you thing.
That's just a me thing.
Yes.
I tend to wander around clubs with a load of toilet paper in my ears because it's too loud. I don't care, I look an idiot, but my ears still work afterwards.
Very true, very true.
So yeah, I mean, it will depend on the other things. It will depend on is exact atmospheric conditions.
Yeah.
If there's something which will make the sound can get sort of focused back down, reflected back down to earth again, which will mean that it'll be louder. If it's coming to you straight and going upwards and kind of being focused down again, then it'll be louder. If the wind's moving towards you, then because the air's moving, the sound doesn't have to travel as far in the air, so it will be louder. So there's all sorts of things. So I mean, people who are yodeling, I think, can be heard sort of across valleys. So maybe up to maybe a kilometre or two if they're very good at yodeling and very, very loud, and it's a very quiet day up in the Alps. And of course, whales, because they make very, very deep, very, very slow vibrations. They can communicate over thousands of kilometres inside the sea.
It's amazing, isn't it?
Especially also because the sound will get trapped inside the ocean because it can't get out into the air and it can't get down into the rocks.
Yeah.
So it doesn't dissipate nearly as much, so it'll travel further. Wow. So yeah, thousands of kilometres if you're a whale shouting in water. Yeah. If you're whispering with someone with a pneumatic drill next door, not very far.
Dave, thank you very much. Now then, we have a caller lined up. I believe we've got Mike on the line. Hello, Mike.
Oh, hello there.
Hello there. You're through to Dr. Dave.
Yes, hello, Dr. Dave.
Hello.
What it is, I'm a security guard, and in the mornings I see the sunrise, but how is it that it comes up from the horizon as quickly as it does, like within sort of 12 minutes?
Yeah.
And I find it quite amazing how quickly it happens. Why is that?
Well, I mean, there's two things. One of them is that the sun is mostly a lot smaller than you think it is. It's only, I'm trying to do the maths in my head, which is always dangerous. It's only about about half a degree across. And it goes around 360 degrees in 24 hours. So that means it will do 15 degrees every hour. So it will probably take about a 15th of an hour. About a 15th of an hour to come up just because the sun's that small. That's only a few minutes, so just because that's just how the sun's quite small and it's moving that fast, so it will come up in about 12 minutes. Quite often the first rising and the very last setting happens extra quickly as well, because you get a sort of magnification effect from the atmosphere, which means that you can actually see the sun when it's below the horizon. and so it tends to slow down just as it gets just above the horizon, and as it goes down it slows down, and then the very last disappearing bit happens very quickly because it's got so far away. This sort of magnification, this kind of bending light around the corner, a bit like a prism, will suddenly stops working so well and the sun just disappears very quickly. A lot of it, I think, is basically just the sun is quite small and it is moving that quickly. But there would be a bit of exaggeration because of this prism effect from the atmosphere, which means you can see it when it's below the horizon.
Does that make sense?
I think he's just explained the eighth wonder of the world. I'll try and remember that and repeat it back to my colleagues. Thank you very much for your help.
All right,
Bye-bye.
thank you.
Bye-bye. Thank you.
Bye-bye. Right, so that's all to do with our sunrise, and it is a wonderful sight. That's the best thing about being up. If you've been up late and going home watching the sunrise.
Yeah, that's when I've seen most of my sunrises.
Yes, me too as well. All right, John in Peterborough says, a question for Dr. Dave. Why do bicycle inner tubes have different valve types? There are 3 different ones of which he knows of. Do different sorts have advantages or disadvantages in comparison to others?
Yeah, I think there's 3 main types. I think they're called Schrader valves, which are the equivalent of the ones you get on cars, which are a bit larger diameter. Car tyres want that larger diameter because you need to pump a lot of air into a car tyre, so you want more space to get it in.
Yeah.
The advantage of those is that if you've got them on a bike, especially a mountain bike, you've got quite a lot of air in a big inner tube, so you want to be able to pump it in quickly. The other thing is that they're compatible with car pumps, so you can just get your car foot pump and put it on, and that makes it easier, and you can pump it up quickly.
Or stop at a garage if you can afford it.
Yeah. Well, be careful. I think you can explode tyres if you put the pressure up too high on those. There are other ones, the Presta ones, which are the very long, thin ones. They're designed to go up to very high pressures. They're often on racing bikes because racing bikes, because they've got a small tyre, you've still got to take the same amount of weight as a person. But it's such a narrow tyre, it's over less area, so you want to pump them up to very high pressures. And also you want to have the least area of tyre in contact with the road because that loses you energy when you're cycling fast and slowly, of course. And so they're designed to take much higher pressures, and they're smaller diameter, so you can use a smaller bicycle pump on them, which is lighter if you have to carry it. And then I think the third one, which is a bit like a shorter version of those, which is an old one, I'm not quite sure if that has any advantages. Most tyres these days are either Presta or Schrader.
All right, OK. Thank you very much indeed. Now then, let's go to the phones again now, because Estelle is on the phone. Hello, Estelle.
Hello, Sue.
Hello, you're through to Dr. Dave.
Thank you. Hello, Dr. Dave.
Hello.
Hello. I've been wondering for years, when you're in an aeroplane, and the aeroplane banks when it's probably got to the airport, and you can see the sea out of one side window and you can see the sky out the other one.
Yeah.
Why do we stay upright and things not fall off the table? And
Yeah, you
bend
think at that angle, because they bank at really quite steep angles. Everything ought to be rolling down to the side of the plane.
I sit there rigid when they do that sort of stuff.
Yeah, I mean, that's a really interesting question. The reason is, do you remember as a kid, have you ever played on a roundabout?
Yeah.
And if it's going really fast, you get thrown outwards to the outside of the roundabout, don't you?
Yeah.
The reason is that in order to go in a circle, you've got to pull yourself in, and the feeling of you being thrown out is called centrifugal force. Yeah. When a plane banks, it's also going around a corner.
Yeah.
So essentially everything is getting thrown outwards sideways, which pulls it back to what feels like downwards, which pulls everything towards the bottom of the plane because you're going around this corner, which cancels out the tipping largely. If you imagine the plane flying around a corner, and the centrifugal force, which is throwing everything outwards towards sort of sideways towards the plane going around the corner, which will pull everything in that direction. It feels like there's this force pulling everything, called centrifugal force, pulling everything outwards, which counteracts gravity pulling downwards. So it feels like gravity, and it feels like it's coming from pretty much near the bottom of the plane if the pilot gets it right.
Right, because you don't feel anything, do you?
No, if the pilot got it wrong, if the pilot wasn't going around a corner and just tipped up on 45 degrees, then everything would fall down.
Oh, right.
But it's because he's going around a corner at the same time, and he judges it so it feels about right.
Oh, right. I think I'm with you.
Well done. So now you know.
Right, well, thank you very much for that. Thank you. I can tell everybody I've been asking who don't know.
That's what we like, Estelle. Yeah. Thank you very much
Thank
indeed.
you, Sue.
Okay.
Bye-bye.
Bye-bye. Peter in Ipswich asks, I've heard of this new dance floor in London, I believe, where the more you jump around and dance, the more electricity is produced. How does this work? Ooh.
I haven't seen it, so I don't know how specifically they've done it. There's all sorts of ways they could have done it. They could have put some kind of piezo thing like the lighters, which would produce a high voltage. I would doubt they've done it that way because quartz crystals is basically this. If you ever get white pebbles on the beach, it's the same stuff as that, and it's really quite brittle. And I'd have thought having people jumping around on it would tend to break it unless you're very careful in how you've designed it. Other things you could do, if you had sort of floated it on a big sort of tank, if you had a big sort of waterbed under the dance floor, when people jumped on bits of the waterbed, it would squirt water out, which if you had a little turbine in it, then it would squirt water out through the turbine and it would generate electricity. Or you could just have a dance floor so that when bits of it go up and down, it just turns a generator. As they move up and down, maybe with a rack and pinion or something, which would generate electricity. I'm afraid beyond that, I'm just speculating, really. So there's various ways you could do it. I don't know which particular one they've used in that dance floor.
Sounds interesting. Sort of place for you to go and search out with your toilet paper in your ears, isn't it? Thank you very much, Dr. Dave. John has called to say if you took a microwave apart, you would certainly die, particularly if it was on.
Definitely if it's on.
Yeah.
There's very high voltage transformers. They transform up to sort of 2,000 or 3,000 volts. And it's not just a few thousand volts, they'll actually produce very high currents as well, and they are very, very dangerous, taking microwaves apart.
All right, something else here, dangerous. Matt in Norwich asks, do you know about the Large Hadron Collider, and will it kill us all?
Okay, the Large Hadron Collider is an experiment they're doing in CERN, which is the biggest physics experiment in the world. They've got a tunnel which has got a big circular tunnel which I think is 28 kilometres across. It straddles between the French and the Swiss border. It goes across the border. Inside this, they've got a little tiny tube which all the air's being pumped out, and they're firing protons at incredibly high speeds, almost the speed of light, round and round this circle in two opposite directions, and then in some places they'll collide with each other, producing a huge, great explosion. And by looking very carefully, well, not a huge great explosion, a very, very small explosion by our standards, but for a proton, it's releasing an immense amount of energy. It's sort of far less than a joule, far less energy than I would release by dropping this pen onto the table. But because it's from one single atom, and normally there's 10 with 23 zeros atoms in a few grams of material. So from a single atom, having that amount of energy is absolutely immense. And by looking very, very carefully at the bits which get thrown off this, the physicists think that they can learn more about the universe, possibly find out what actually causes gravity, because people have some theories, but no one's actually proved them. There's a theory that there's a particle called the Higgs boson, which is actually giving things inertia rather than gravity, and why it's hard to move heavy things, because physicists don't actually really understand that. So they're trying to do this. Some people have suggested that possibly you could make a minute black hole which would swallow up the Earth. But this is actually immensely unlikely, because although these collisions are far more powerful than anything that we've made on Earth, which humans have made on Earth before, all the time there are particles coming from space smashing into the atmosphere, millions and billions millions and billions of times more energy than that. So they're coming in all the time. It's cosmic rays. Most of them are sort of that sort of energy or lower, but some of them are have ridiculous amounts of energy. Sort of with one ion nucleus, there's enough energy to actually heat up significantly a lump of water, which is a ridiculous amount of energy. But because this is happening all the time, then the kind of collisions that are happening in the Large Hadron Collider are happening all the time naturally, and the Earth hasn't been destroyed in the last 4.5 billion years, so we don't think it's going to in the next few years.
Oh, good. Well, that's a comfort then, isn't it, to some of us? Can you ask how we get storms in the middle of winter? I always thought air had to be hot and humid to create storms. Dave?
Basically, air does have to be hot and humid to create storms, but the important thing is it's hotter and more humid than the air around it. And so in the winter, the way we get storms is you get air mixing. Because in the winter, the air up near the North Pole there's almost no sun shining on the North Pole. So it gets really, really, really cold. But still near the equator, the air's really quite warm. And so especially with coming up along the Gulf Stream, you get lots of warm water, which warms the air. And you get lots of warm, humid air coming up from the southwest. And then if this meets the cold air coming from the far north, then it's going to rise very quickly up above the cold air, and this is going to suck in more air to fill up the space, which will rise again and again. All the humid air is going to, as it rises, it expands and gets cooler, and so the water condenses as it cools down and forms rain and rains on you, and so. Yes, you do need warm air, but you're getting it from it's moving all the way across the earth from warmer places at that time of year.
All right, that's answered that one. Right, our next question. How do dolphins and other animals steer themselves in the water?
Not really my strong point. Definitely dolphins have a very sophisticated form of sonar. They make the clicks you may have heard of dolphins make. It's ultrasonic, higher than the pitches which you could hear with your ears. They tend to slow them down so you can hear them. And they use that as a sonar, so they bounce that off things. So they could probably they can probably use that to see the shape of the ocean floor to navigate, definitely near coasts. So they'll be able to build up a picture of what's around them by making clicks and get an idea of what's going on. I'm not sure if they do long ocean journeys or not. Because I would be surprised, unless the high-pitched sounds aren't going to go very far, so they wouldn't be able to reach the bottom of an ocean, so they wouldn't be able to be like that. Because
there's been the cases, haven't there, of dolphins and whales sort of getting stuck in, coming up river and getting lost effectively.
Yeah, it's been suggested that might be to do with very loud noises underwater, which essentially deafens them, and so and if they can't hear, the sonar doesn't work, because sonar works by sending out pulses of sound, and then listening to when they get reflected and what directions they get reflected from. So if a dolphin or a whale can't hear, then they're not going to. They basically can't see. But no one's really sure why it's going on. Whales also have a lot of whales have a sonar navigation signal to find their prey and to find their way around.
Sure.
I don't know whether they actually, if they come up to the surface, I mean, basically how animals navigate is a question which we're not sure of. It's not really my area, so I don't really want to say too much more.
Hi to Keith, and also another question about outer space. Dr. Dave, does centrifugal force work in outer space?
The simple question is, yes. It does. Centrifugal force isn't a real force. It's what's called a pseudo force. It's basically things, if they want to carry on going in a straight line. And in order to make them go in a circle, you've got to pull them inwards. So if you've got a piece of weight and it's swinging around a string, the string's pulling the weight inwards. Now, if you were sitting on that weight and that was spinning round and you couldn't see anything else, it would feel as if there was a force pulling you outwards away from the centre of the circle. And so centrifugal force is what it feels like if you're on a spinning object and you didn't know you were spinning. It just feels like everything is getting thrown outwards. That's because it's trying to go in a straight line. But it's not. So it's not a real force. It's not like gravity or an electric field or something. But it's just there because if you don't know you're turning, sometimes it's a lot easier to do maths in a problem, or a lot easier to think of something as if the world isn't moving and just everything's getting thrown outwards by a force called centrifugal force. And that's got nothing to do with gravity or air or anything, so it'll work anywhere anything's spinning. You can imagine a force called centrifugal force.
All right, Tom in Lexington, Colchester, said, I've just heard Dave talking about his dance floor. It just so happens I saw a programme about this, and I can confirm that they do use piezo, as Dave has said.
OK, so it's a piezo transducers like the gas lighters, which is interesting.
Yeah. All right, Keith in Kettering, question, is it a coincidence that the height of the Cheops multiplied by 1 billion corresponds to the distance between the Earth and the Sun?
To be honest, I don't know. I would be surprised if it wasn't if it wasn't a coincidence. I think Cheops is a pyramid in Egypt, and working out how far away the Sun actually is a very difficult problem It wasn't done until relatively recently, in the last 300 or 400 years, by very carefully studying Venus in two different parts of the world as it moves across the sun. And that will happen at slightly different times of day, because you're looking at a different angle from the different times. You're looking at a different angle from different sides of the Earth. From that, they could work out how far away Venus was, and then how far away the sun was. So I would have thought that unless the Egyptians were getting information, were very, very clever, I would have thought it was a coincidence, yes.
OK, thank you very much, Keith, for that one. Now then, since space is not a true vacuum, can any sound be heard?
OK, and normally, I mean, we do say that you can't hear any sound in space because it's a vacuum, and sound is vibration travelling through air. If there's no air there, then you can't have a vibration moving through nothing, so you won't hear any sound. Now, there are some air particles in space, and you probably could transfer a vibration through it, but because there's so few, there's only a few in every cubic metre. In order to be able to actually transfer a force like this, you would need huge plates, move them very gently, and incredibly sensitive force measuring devices, and you probably wouldn't be able to feel the force. Because it would be less than the force which light applies to things, because light actually applies a very tiny force, which people are trying to use in order to sail around the solar system with big mirrors, in order to move satellites around the solar system. So, yes, in theory, with the very, very few atoms which are there, you could transfer a sound, but in practice, I don't think you'd be able to measure it.
All right, thank you very much, Dr. Dave. We had a fantastic email in from Gerald. Thank you very much for this. With all the advances in digital broadcast, why is the online Listen Live and the DAB radio so far behind the FM signals that pips on the hour are several seconds behind? Tess with ever-fast computers often has the faster machine with the most expensive and newer hardware, lagging behind slower machines with older hardware. But that is not consistent, even when it's making sure the minimum of the background tasks are still running. On Freeview, the time delay can be as much as 2 complete sentences with 4 systems all out of sync. Perhaps Dr. Dave knows the correct reason why.
I mean, there's various reasons why these things, there's a delay. A lot of it is just that they're trying to jam more information in the same space. In the space which you get sort of 4 or 5 TV channels in conventional analogue signals, there's a lot more in Freeview. I don't know what the ratio is. It's at least 4 or 5 times more channels in the same amount of bandwidth, in the same amount of radio frequencies. In order to do this, they're throwing away information. There's very clever computer programs which they look at a TV picture and see what's changing. They attempt to guess where objects are going to move and then find out where they actually do, and then fudge it a bit. And then only I'd say, okay, if there's an object moving across the screen, we'll say it's moving across the screen, then we'll only transmit anything which isn't doing that. And this all takes time, and it also involves looking at over a period. In order to do that well, you need to look into the future a bit, as it were. You can't really do it immediately from just what's happened in the past. You need to look a bit into the future, which eventually means everything's got to be behind in order to be able to look into the future in order to transmit it. So all these things take time and are slow, and it adds to the delay. The other thing with computers, if you're listening to it live, they cache. So they'll keep a certain amount of data, several seconds worth. They're always reading ahead. So if the signal drops away for a few seconds, it can keep playing what it's got in its store. It's why it says caching when you start playing on things like the iPlayer. Yeah. It's sort of having a store of information in the future, so you're listening behind, so you don't get so many stops, because then all of a sudden lots of data will arrive at once and it can fill its store back up again. So you probably could reduce that time it caches, but it would be a lot choppier. So different computers might be using different lengths of cache.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.